Reduce children when you're talking, please.
Yes. Right. So in the last class, we talked about particle accelerators, and so basically, particle accelerators are huge. They're like they use charged particles, and they drive these particles at very high speed, almost close to the speed of light, like almost 99% speed of light. And then so you have like a ring, and the particles are accelerated in that ring through electric fields, and they are smashed into each other, or they are smashed onto a target. And then because these particles are accelerated with such high speed, there's a lot of force generated and a lot of energy generated, due to which new particles are formed, or the particles are broken down further. And so with the help of various experiments, we can study these new particles, and we can like further investigate into smaller particles.
Oh, okay, thank you.
Good evening, everyone. Sorry that I joined late. There was a meeting going on. Please continue, Devanji.
Right. So does anyone have any questions from the last session? Okay, so before moving on to today's session, we'll quickly discuss the answers for the last quiz that we gave you. Uday, would you like to start?
Yeah, sure. Actually, when I was restarting, the window got closed. Just give me 1 minute. I'll bring it up again. Or if someone else has it open, the quiz, either you
Yeah,
or
I'll
Pancho,
share
can you share the
the.
screen?
Sure, I'll share it.
Madhav, the quiz was shared at the end of the last session, so you must have received it if you were there. But if you weren't, then don't worry. We'll also share the quiz with you later as well. So you'll be able to access it soon.
Okay.
1 minute. Is it visible?
Yep.
Okay. So the first question is, for what purpose do we use the standard model? Or would anyone like to answer this? Whoever filled it, maybe.
Uh, Alia, you can go ahead.
Yes. So I think one of the reasons we use one of the purposes we use the standard model for is to explain the link between fundamental particles and the fundamental forces.
Yep, that's correct. That's one of the valid points. So do you think there are any other points that are also valid amongst the five listed here?
To formally organize the fundamental particles as well.
Yeah, that's correct. So those are two correct points. Anyone else, if you think there are any more points, or do you think those are the only two points that are correct? Anyone?
I think to make predictions about theoretical particles as well.
Yeah, great. One of the correct options as well, because it also, the standard model also allows us to make predictions. One of the most famous examples is the Higgs boson, which was first theoretically predicted by the standard model, and then it was confirmed as well. Um, someone said the last one as well. I'm sorry, but that's not correct, because currently the standard model only explains matter that is known to us. So the standard matter, such as photons, fermions, and the other types of particles that we discussed earlier. So right now, dark matter is actually not a part of the standard model, so we cannot explain the composition of the dark matter with the standard model. So I hope that's clarified then.
Is the third one correct?
The third one, to study the properties of atoms and molecules. That is not correct, at least directly, because the standard model is concerned with particles, right? It's concerned with the subatomic level. And when we're studying the properties of atoms and molecules, we usually deal with the periodic table or other concepts of chemistry. So you could say that we are studying the atoms in a very indirect manner, but that would be stretching the definition a bit. So when we're talking about the purpose of the standard model, it's to study the fundamental particles and not atoms and molecules. I hope that answers your question.
Yes.
All right.
Next, which of the following points are true? Anyone would like to try this? Then will you explain it?
All right. I think Alia was raising a hand.
Okay.
Yes, so I think the first and the third statement is correct. Quarks interact with all fundamental forces, and leptons interact with all fundamental forces.
Okay, so you got one of them right. Quarks do interact with all fundamental forces, so that's correct. But the third one is actually not correct. Leptons do not interact with all the fundamental forces, right? They don't interact with the strong nuclear force, so that's why the third one is incorrect. Uh, I think Madhav has also raised his hand. I'm not too sure, but
Yeah,
Madhav, yeah, go on.
yeah, I wanted to say that. Second one is also correct.
The second one says all quarks are charged particles. Right. So, does anyone want to contradict that, or does everyone think that it's correct?
No, I don't think it is correct.
Okay. So, do you think any other option is the right answer?
Yes, I think all leptons are charged particles.
All right. Okay.
I believe that is incorrect because leptons have neutrinos which have neutral charge. So
Yes.
it's not.
Yeah, that's a good point. So the last point is actually incorrect. That, as you said, neutrinos are a species of leptons, and they, of course, are neutral. And the second point is correct. All quarks are charged particles. So those are the two right options. So yeah, good job there.
So next question, which boson carries the weak force?
Costa writes W bosons and Z bosons. Yeah, that's right. It's carried by these two bosons, W and Z. So good job. Anyone who has any doubt in this question?
Okay, then next question was the strong force is strictly attractive. True or false?
Yeah, go ahead, Samya.
It would be false as it is repulsive at shorter distances.
Yeah, perfect.
Right. Then next question was which type of quark is used by LHC for studying matter and antimatter?
Yeah, Urjit, you can go ahead.
It's the bottom quark.
Yeah, right. And it's also known as the beauty quark. Then next was neutrons are used in particle accelerators. True or false? Anyone would like?
Vidush, did you raise your hand for this question?
Yes, I
Yeah,
think
go on
it's
then.
false because we had been told that only charged particles are used in particle accelerators, but neutron does not have a charge.
Right, that's correct. Since neutrons can't be accelerated by electric fields, we can't use neutrons in particle accelerators. Okay. So maybe we can start with the session now.
Yeah, I guess so.
Yeah, I hope all of you enjoyed the quiz, and this is going to be an integral part of our every session. At the end of every session, we'll have a quiz. And like it was explained to you last time, we will look at your performance for all the various sessions, and then the best 10 performers will be, we have a surprise for you. All right. So now, yes, Uday, let's begin with the session for today.
All right. So today, in the last session, we talked about particle accelerators. We talked about how accelerators work, and so this time we'll delve deeper into the theoretical realm of particle physics once again, and we'll talk about a new concept known as spin. So I'll just share my screen. Just give me a second. Yeah, so before I go on, I want to hear from you guys. So, spin, if you're interested in particle physics, then I'm sure it's a term that you have heard in the past as well. It's a very common, it's a very common term that gets thrown around when we're discussing particles and particle physics in general. So, does anyone have any general idea about what spin is, and would they like to share it? Anyone? Just any vague idea would also do. Just we're trying to discuss. Okay. Oh yeah. Arnav, yeah, you can go ahead.
I'm not sure, but I've heard of spin in the context of chemistry. So basically describing the orientation of an electron within an orbit.
Right. So that's a good point. So when we're dealing with chemistry and we're dealing with electrons, as you said, in their orbitals, spin comes up quite a lot, and we'll go into how that works. But that's one of the areas where spin is relevant. I think someone wrote in the chat.
Angular momentum.
Angular
Was
momentum. Okay, so angular momentum is, yes, I would say it's connected. It's one of the terms that often gets paired with spin, but don't equate the two. So we'll talk more about how spin is actually not angular momentum, but don't think that spin is the angular momentum. That's not correct, because angular momentum is describing the momentum of something that's in circular motion, right? So I uh, take uh, if I take a ball and I attach it to a string, and then I start moving it in a circle, then it's in circular motion, and the momentum that my ball has is known as the angular momentum. So in order for something to have angular momentum, it's necessary that the object needs to be in circular motion. However, when we'll talk more about this particular topic, we'll understand that that's actually not what's happening, which brings us to a good starting point for the discussion, that what is spin. So one thing that you should always keep in mind is, even though particles have spin, they aren't actually spinning. So that's one of the major misconceptions that I had when I was younger, because it's very easy to assume, and it's very natural to assume, that if someone says that this particle has a particular spin, then you get the idea that the particle is something like the spherical body that is actually spinning. But that's actually a wrong way to understand spin, because one thing that you must understand is that these particles are minute. They're tiny in nature, right? They go down to like just amazingly small sizes. It's not even possible to uh, properly define how small they are in words. So in order for something so small to be spinning, they need to be spinning at a very high rate, so they cannot actually be rotating in a realistic manner. So that's an idea that you should have in mind, that a particle spin is not a spherical body rotating. That's not correct. A spin is actually something else. And what is it? Well, it's a little hard to define. So I think that's one of the reasons why we waited for so many sessions to actually introduce this topic to you, because spin is one of the most complicated topics within the domain of particle physics. In fact, Pantha had also mentioned it in the last session that there are a lot of scientists and particle physicists who still don't understand what exactly spin is. So even though it's something that we use quite a lot in order to understand the particles, it's not something that we have a complete understanding of yet. So when usually, if you look up what spin is, it's any website or any article would tell you that it's an intrinsic property. So it's something that exists just because it exists, right? And that's not very helpful to us, because that's usually not what we try to do in science, right? If something exists, we try to find out why it is existing in that manner. However, what happens is that when you're trying to boil something down to its true state, there often come some dead ends, right? So it's almost as if saying that you start asking about why does this phone exist, for example. So one would say that, okay, the phone was manufactured by some company in China. Why was it manufactured? It was commissioned by a company called Apple in America. Why was that? Why did that happen? Because the company was founded by Steve Jobs so and so years ago, and so on. So you can go on to a line of reasoning, right? And you would at the end reach a point where you would think, okay, why did this thing happen? Why does anything exist after all, right? So that's the big question we have, and it gets slightly philosophical here, that at the end when we boil it down, we reach fundamental questions where we're not able to explain why something is happening by logical reasoning. And that's something that also happens in a more scientific sense in particle physics as well, because when we're dealing with scales that are so small, we try to explain everything, right? So first we started off with the idea of an atom, then we broke the atom down into protons, neutrons, and electrons. Then we further broke down protons and neutrons into quarks, and now we're trying to study the properties of quarks. So when we're saying that quarks are something that are fundamental, we are trying to study something that cannot be broken down further, right? So if someone asks you, why does a proton have a charge of +1, you can tell them that the proton has a charge of +1 because it is composed of 2 up quarks and 1 down quark. But if someone asks you why does an up quark have a charge of +2/3, then that is a question that you cannot really answer very well. It simply exists just because it exists, and that's what the word intrinsic means. Uh, I think there's a question in the chat. I'll just take it up after this slide. So that's something that exists just because it's there. That's what the word intrinsic really means, and that's one of the properties of spin. It's an intrinsic property, so it cannot be explained by other supporting theories, and we cannot break the concept down into parts in order to understand the whole, because it's something that cannot be divided. So that's the first thing that I wanted to clarify, that spin is an intrinsic property. It's something that's rooted at the fundamental level, and it's something that exists just because it's there. We don't have a very good explanation about where it came from, and that's something we're still working on. So firstly, what is spin? So in a more scientific sense, spin is basically a property that particles have that explain why those particular particles have electromagnetic properties. right? So uh, in the last session, or I think, uh, yeah, we just very briefly skimmed over, not in the last session, but I think in the last to last session, we just briefly skimmed over how a particle known as, how a field known as the Higgs field gives rise to the masses that the particles have, right? So the mass is a property that every particle has, or a lot of particles have, that can be explained by the Higgs field. Similarly, electromagnetism is a property that a lot of particles have, right? So we discussed how certain particles, they have electromagnetic properties. Oh, just one second. Have certain electromagnetic properties that they exhibit. So the spin is basically allowing us to understand why those electromagnetic properties exist. So and how they do that, I'll cover that in the next slide. Before that, I'll just take up some questions one by one. So first, Alia asked, what is angular momentum? Okay, so angular momentum is actually a concept from mechanics. So it's not a concept from particle physics. And Alia, do you understand what momentum is? Not angular momentum, just normal momentum. Do you have an idea about what that is? Is Alia with us?
Alla, you here in the meeting? Oh, she is here, but she's not.
Yes.
I'm
Oh,
muting her.
okay, so I guess we should wait for her to take up her question. So, Urjit, you had also raised your hand. Do you have a
Uh,
question?
yeah. So my question is that when you said that particles possess electromagnetic properties, so do you only mean those particles who actually mediate electromagnetic properties, or are you talking about something else?
Right, that's a very good question. So, when we talk about particles mediating the electromagnetic force, then we only talk about the photon. So that's a separate argument altogether. But here we're not talking about the electromagnetic force. We're talking about simply electromagnetic properties, and largely just the ability or that particles have to generate magnetic fields, right? So that's something that I'm going to talk about in more detail. But that's a good clarification that you should have. That here we're not talking about the electromagnetic force. We're talking about the capacity that particles have to generate magnetic and electromagnetic fields. So those are similar but different topics altogether. I hope that answers your question.
Yes, thank you.
All right.
I think Anish had also raised her hand if he's here.
Yeah, and
Alla's back.
okay. Anish, do you have a question? Uh,
Oh no.
Okay, so Alia, I hope you're back now. Uh, I saw one of your questions. Do you?
Yes, yes. Sorry, my light had actually gone.
All right, that's all right. So you asked, what is angular momentum? Right. So before I
Yes.
explain what angular momentum is, I want to ask you: do you have an idea of what normal momentum is? Not angular momentum. When we just say momentum, do you know what that is?
Yes, momentum basically defines the speed or we can say velocity of how fast or slow something goes.
Okay, so when we talk about momentum, just general momentum, the general idea that we have, or the formula, so to say, that we have in physics is the product of the mass and the velocity, right? So whenever something is moving, whenever something that has mass is moving through a given space, it's moving at a given velocity, right? Which is the displacement upon time, and when we multiply that velocity with the mass, we get an idea of that object's momentum. So the momentum is basically something that is telling us, that is relating the mass of an object with the velocity of that particular object. So that's what happens in normal motion. Like if I throw a ball sitting here right now in front of me, then I would be able to measure its angular momentum since it's moving in normal space. But that's just very fundamental. That's very basic mechanics. But there's a slightly different field, which is also known as circular motion, right? So when we're throwing something, if I throw something from here in front of me, then that's an example of normal motion, a standard motion, because it's not repeating itself, right? But if I, for example, if I give you the same example, if I tie a ball with a rope and I hold one of the ends in my hand and I start moving it and it starts rotating in a circle, then that becomes an example of circular motion. Or let's say you have a car that is moving in circles about a roundabout, right? So it's continuously moving in a circle, then it's also an example of circular motion, right? Because it's not moving in a straight line, it's moving around the circumference of a circle. So that's what circular motion is, and here we are concerned with slightly different properties, which correspond with their standard properties as well. So where we have momentum in normal motion, we have angular momentum in circular motion. So if I won't go into the very deep details right now, but what angular momentum is basically telling us is the momentum of an object when it is moving in a circle, right? So if you want to calculate the angular momentum, you multiply the mass of an object with its velocity and the radius of the circle that it's moving in. So when we were talking about momentum, normal momentum, we were multiplying the mass with the velocity. But here, when we're talking about circular motion, then we also have to take the radius into account, because that's our important factor when we talk about the motion in a circular sense. So that's what angular momentum is. It's the product of mass, velocity, and the radius of any object that's moving in circles or moving in circular motion. So I hope that answers your question.
Yes, thank you.
All right. So, any more questions right now, or should we move on? Anyone? Any questions about what we've discussed so far?
I think we can move for
Okay.
now.
Yeah. So let's move on to the next slide then. So now let's talk more about why we call spin spin. So I discussed earlier on that it's a very common confusion for students to have, for them to think that when they hear the word spin, they imagine the particle to be actually spinning. And when we're naming something, we usually want the name to be self-explanatory, right? So why did we name dark matter dark matter? Because we had no idea what dark matter is. So we called it dark matter in order to signify that, because we can't see it, we can't observe it directly. So usually when scientists name things, they try to name it so that things can be understood intuitively from the name itself. So why name this property that particles have spin when particles actually aren't spinning? So that's what I want to talk about right now. So the reason why we call this property spin is because when this property was first discovered, or when it was being researched, then scientists actually thought that particles were spinning. So that's the first theory that they had, that they thought that particles were actually spinning, and they started calling it spin. And later on, it was discovered that spin is actually the particles actually aren't spinning, but they still decided to stick to the name because uh, they had been using it for very long, and they decided to stick to it. So let's talk about why they thought particles were spinning in the first place. Now, if you remember from the last session when we were talking about particle accelerators, we talked about how when some charged object is moving, is experiencing force, then it creates a magnetic field around it, right? So we discussed how when something that has electric charge and an electric field is moving, it also creates a magnetic field, right? That's why we call it the electromagnetic force and the electromagnetic field and so on, because they are both interconnected. And that's why uh, we think of the electricity and magnetism as being sort of two sides of the same coin. So that's the starting point that physicists had, particle physicists had, that this was a theory that had been established by the scientist named James Maxwell many years back. So what scientists were basically doing was they were looking at particles, and they saw that the particles were generating their own magnetic fields, right? Even if there weren't any photons mediating the electromagnetic force, the particles could themselves generate an electric field, a magnetic field. So they wanted to figure out why that was happening. Now, we already knew that the particles were charged, right? We already knew that the electron has a negative charge. We already knew that the photons have a positive charge, and consequently, we also figured out that quarks have respective negative and positive charges as well. So we already knew about the charges that particles have, but we did not know why they were generating magnetic fields. So there's a difference between charge and electricity, right? And there's a difference between current and charge. Just because something has charge doesn't mean that it has electric current. It's only when that particular charge starts moving when we call it current, right? Because how do we define current? We define it as the quotient of charge and time. So charge upon time gives us current, electric current. So we already knew about the charge that particles have, but just because something has charge doesn't mean that it must have a magnetic field as well. The charge must be moving in order for it to generate an electric field, and when something generates an electric field, it also generates a magnetic field. So that's the idea that the scientists had, that okay, if the particles have charge and if they also generate magnetic fields, then they must be moving through space in order to generate that magnetic field, right? And that's a pretty good assumption to take, because we already knew about the properties of electromagnetism, as I discussed, and we already knew the particular details about the charge that the particles have. So they thought that the particles must be moving in order to generate magnetic fields. But when they actually observed, just a second, we'll take up the question. So when they actually observed the particles, they saw that the particles weren't actually moving from point A to point B. So how else can something be moving in order to generate a magnetic field? Well, here comes circular motion again. And that's where the topic of angular momentum also kicks in. That what happens with circular motion is that an object doesn't need to be moving from point A to point B. It can be moving around a fixed point in a circle, and it would still count as motion, right? Because you're still constantly changing your direction, you're still constantly going through motion. So they thought that if particles aren't actually moving from point A to point B, they might be rotating in order for them to generate magnetic fields. So they thought that because we know that the charge isn't moving from point A to point B at some velocities, but because it is generating magnetic fields, it must be rotating in order for it to have motion. And because that charged particle has motion, it's generating a magnetic field. So that's why scientists started calling it spin, because earlier they thought that the particles were actually spinning in order to generate magnetic fields. So that was the first idea that they had. But then what happened was that uh, then that theory came up, which I explained earlier, that for something so tiny to actually move in circular motion and spin and generate a magnetic field, they would have to move at speeds that often exceed the speed of light, which is known to be the speed limit, right? So we scientists then figured out that okay, particles aren't actually spinning, because in order for them to spin and generate a magnetic field, that would be a very absurd idea, because they would have to spin at extremely high angular momentum. So that's where angular momentum comes in. That they would have to move at extremely high angular velocities in order for these charged particles to actually create magnetic fields around them. And then they came up with the idea that spin is actually an intrinsic property. So intrinsic properties, as I explained, are properties which basically exist because they are that way, right? So the idea was that the particle is behaving as if it is spinning, but it's not actually spinning, which is a bit tough to get your head around. But bear with me for a second here. That it's as if you're saying that the particle is actually spinning, so it's exhibiting all the behaviors it would if any charged body was spinning, but it's doing that while actually not spinning, which is why it's an intrinsic property. It's happening just because it's happening. It's some property that the charged particles and that the fundamental particles just happen to have because the universe is just made in that way. And that's what spin is. It's basically a concept that allows us to understand why certain particles have magnetic fields around them. So this is, again, as I mentioned, it's not the easiest topic to understand, and I'm sure you have a lot of questions, so I'll take them up. I think Ayan had posted a question in the chat. It says, if a charged particle is vibrating, would it generate a magnetic field? Yeah, the short answer is yes. If a charged particle is vibrating, if it is oscillating, then it would be generating a magnetic field. However, there are a lot of details that go, yeah, that we don't know which particle we're talking about and what kind of vibration we're talking about, but in conceptually you can think of it that way.
If particles are simply vibrating, if charged particles are simply vibrating, the oscillation, that oscillation creates your electromagnetic waves or light. Light is basically your oscillating charged particles. Every photon is emitted by due to that. So yes, an oscillating charged particle will create a magnetic field. In fact, the way the magnetic field and the electric field are produced, that they can extend out to infinity because they can both help each other move forward.
I hope that answers your question. Urjit, you had also raised your hand.
Yes, I had a question related to spin. As in, if we say that magnetic field is generated by spin, so let's say one atom attract another using magnetic field, and
One atom.
then so are we talking about the atoms or the or actually the fundamental particles?
Okay, so that's again a good question. And here again, you have to differentiate between electromagnetic force and electromagnetic properties, right? So if when you're talking about atoms, if atoms can attract other atoms because of charge, right? And that's what happens in ionic bonding as well. If one particle is more positively charged than the other, and the other particle is negatively charged, then then the particles would come closer because of electromagnetic attraction. But here, when we're talking about spin, we aren't talking about the electromagnetic force here. We're talking about particles generating magnetic fields. So we're talking about how the particles would be generating these fields independently and not in terms of electromagnetic forces. So again, as Pantha also mentioned earlier, that if something is oscillating and vibrating, then that's a different story. But spin is telling us a more fundamental property about why the particles have some fundamental properties that they do. Pantha, do you want to add something to that?
No, it's okay. It's basically that only. There's nothing new that I can add right now.
Okay. Vidush, do you also have a question?
Yes. So I just wanted to confirm the definition that I've created in my mind about spin. So basically, by what I'm understanding, spin was thought to be a property that actually gave the particles that helped the particles to create a magnetic field around them. Um, so they are not actually spinning, so we just recognize them as it's some property. We don't know what property it is, but it's helping the particles to make a magnetic field.
Yeah, that's largely accurate. So what it's basically doing is that we're saying that if a charged body would be spinning, then it would be creating a magnetic field. Similarly, in the context of particles, they are generating magnetic fields that they would if something of that particular charge would be spinning, but in actuality they aren't actually spinning, they aren't actually physically rotating. So that's the general idea, that spin is a theoretical construct that allows us to understand why those particles are generating magnetic fields in the way that they are, but they aren't actually spinning. We're just thinking of them as exhibiting a spin in a theoretical sense and not in a physical sense. Okay. Anyone else? Any other questions? Mm, okay. So if not, we'll move on. Feel free to uh, drop any questions in the chat as well have if you have any queries. Okay. Someone sent something.
Allah asked something.
Okay, so spin is basically the angular momentum of something. Okay, so that's the point that I wanted to clarify as well. That spin is actually not the angular momentum, because spin is not actually telling us some the properties of circular motion, right? So, and spin, I don't mean spin in the literal sense. I mean the spin in the context of these fundamental particles that we're talking about. So spin is not the angular momentum of particles. It's basically a number. Spin is basically a number that we assign to uh, different uh, different fundamental particles in order to understand the properties that they have in terms of their um, capacity to generate magnetic fields. So we also call spin intrinsic angular momentum sometimes, but again, just keep that in mind that it's not actually telling us about circular motion, because particles aren't actually spinning. It's a theoretical idea that we have. So I hope that clarifies a bit. Vidush, do you have a question?
Yes. Sorry, I got disconnected during that time. I I understood what you said. So we are just left with the name spin. So we do not know what exactly spin is, but we know that it helps making a magnetic field. Is that correct?
Yeah, I think that's pretty accurate. So spin is again, it's an intrinsic property, right? So you can think of it that way, that we don't know what spin is because it seems to be there, because the universe seems to be coded in that way. So spin, we're left with the name because spin is actually the word spin actually gives us an idea about what the particles would be doing if they would rotate, but that's actually not what is physically happening. So I think that's a generally good understanding that you can have of spin.
Okay.
Samaya, I think you had raised your hand. Do you have a question?
I just wanted to confirm that the if the particles were actually spinning, then it would make sense, but they're not actually spinning, right?
Right. So two things here. Firstly, when you say that it would make sense, there can be two ways in which it would make sense and it would not make sense. So what would make sense if the particles were actually spinning is that we would have an understanding about why those particles are generating magnetic fields. So if they were actually spinning, we would be able to like explain why those particles are generating magnetic fields based on very simple physics, based on general electromagnetism that we already know. So that's something, and that's why we still that's why scientists started calling it spin, and that's one of the reasons why we still call it spin, because it gives us a theoretical idea. So that's one part that would make sense. But what would not make sense is for the particles to actually be spinning in the first place from a mechanical sense. So what happens is that if something needs to spin, again, it needs to have angular momentum. And for something so tiny to be spinning and be generating the magnetic fields that we have observed, then the particles would need to spin at extremely high velocity. So as I mentioned earlier as well, some of those calculations go well beyond the speed limit of the universe, which is the speed of light, 299 million meters per second. So that's the part which makes no sense, because it's not physically possible for those particles to be physically spinning and creating magnetic fields. And that's why we know that the particles aren't actually spinning. So you can think of spin as something that would make sense only in the theoretical sense, but don't think of them as being accurate in a physical sense. So I hope that answers your question, Samaya.
Yes, thank you.
All right. Any more questions, anyone? Okay, so if not, then let's move on to the last slide here. Let's talk a bit more about the details of spin. So when we're talking about spin again, almost every fundamental particle has different spins. So when we're talking about electrons, we usually distinguish the spin that an electron has as spin up or spin down. And when we talk about photons, then things get more complicated. And when we talk about other particles, then the definition of spin gets further complicated. So let's stick to the electrons for the time being. So the electrons, as I'm sure you know, are charged particles, right? Electrons have an electric charge of -1 coulombs. That's and because of that, electrons are also generating magnetic fields, and that's why electrons have spin, right? And here's a concept known as spin up and spin down. And this is actually where the point that I think Arnav had mentioned also comes in, that electrons can either be spinning up or spinning down. And what this means, again, don't think of it in a physical sense. Electrons aren't actually going up or down. That's not what's happening. What we're basically saying is that if the electron were to spin, would it be spinning in the clockwise direction or in the anti-clockwise direction? So think of it this way: if something was spinning, if we had an electric charge and we wanted to generate a magnetic field with it, if we move it in a clockwise direction, it would generate an electric current upwards, right? So you might have heard of this rule called the right hand thumb rule, which basically says that if you hold your hand in sort of the thumbs up position, then if the direction of your thumb would point to the direction in which your charge is moving, and the direction in which your hand gets wrapped around would give you the direction of the field itself. So here, when we're basically talking about the electrons, we are saying that the electrons are generating a magnetic field, right? So is it generating a magnetic field in the upwards direction or in the downwards direction? And when we have an understanding about that, we can say that, okay, if it's generating the field in the upwards direction, or then it would be moving anti-clockwise, right? Because that's what the rule tells us. If it's going upwards, it's going anti-clockwise, and if it's going downwards, it's going clockwise. So again, the electron isn't actually spinning, but the electron is generating a magnetic field that's going in a particular direction. So the spin basically tells us that if the particle or if the electron was actually spinning, then which direction would it have to spin in order to generate that electric field, or sorry, that magnetic field? So in which direction should the electron spin so that the magnetic field that is generated is either upwards or downwards? So that's what spin up and spin down really means. That's just uh, us trying to understand the direction in which the electron generates a magnetic field based on based on our understanding of how uh, the right hand thumb rule works and how charges generate electric currents. So when we talk about electrons again, they can either have a spin of plus 1 by 2 and minus 1 by 2. So those are the valid spins that an electron can have. Now you may be tempted to ask that why is it that way? What does 1 by 2 even signify, and what does this number even mean? And if I were to explain this concept to you, in all honesty, it's something that I don't understand completely as well. And we would end up spending a lot of time on this topic. So I won't go into the details right now. So you can again think of it. For one thing that you can understand is that the plus and minus again is referring to the direction. So that's why the electron has spin up and spin down states, because the plus 1 by 2 and minus 1 by 2 is basically giving us the idea that an electron can generate magnetic fields in two directions, right? Similar to a bar magnet, for example. It's always going from north to south, but the magnet can be pointing upwards or downwards. So that's one thing that you can understand, that the electron is generating magnetic fields in two directions. That's why it has two values, which is plus 1 by 2 and minus 1 by 2. And regardless of that direction, the amount of the magnetic field that is generated, or the magnitude, would remain the same. That's why the number, which is 1 by 2, remains constant. It's just that the other number becomes negative because it's happening in the opposite direction. So that's one understanding that you can have. But why is it actually 1 by 2, and what does that number even signify? That's a concept that I'll leave to you for a bit of further reading. So as I mentioned as well, it's not a topic that I understand completely. I'll have to admit that. So that's something that you can try to learn on your own and try to read a bit and understand that. So again, one more thing that I'll mention is that if you are genuinely curious about spin, then you can also look up an experiment called the Stern-Gerlach experiment, which was basically an experiment that was done a couple of decades back in particle physics that basically gave rise to the idea of spin. So if you think that this topic is intriguing to you, then you can look it up and try to understand what the Stern-Gerlach experiment is. So that's again, that's a point of further research for you. So that's it from my side for spin. If you guys have any questions about spin right now, we can take them up. Otherwise, we can move on. So any questions, anyone?
I think Vidush has his hand
Yeah,
raised.
Ritesh, go ahead.
What difference would it make if the electron, theoretically, of course, is spinning in clockwise or anti-clockwise direction?
So the only difference it makes is the direction of the magnetic field that is generated, right? So if it's spinning theoretically, as you also said, if it's spinning in an anti-clockwise direction, then the direction of the magnetic field that is generated, it would be upward. So magnetic field as well. Magnetic field is a vector, right? It's not a scalar, so it's not it also has a direction. That's what vectors are, something that has magnitude as well as direction. So if the electron was spinning in an anti-clockwise direction, then the magnetic field that's generated by the electron would be in the upwards direction. And if it was rotating clockwise, then the magnetic field that is generated by the electron would be in the downwards direction. So that's
Does
the only difference.
does that mean something, or is just a name? Magnetic
It
field up
does.
and down.
No, it does mean something. So the thing is, you think of it this way, right? So let's say you have a magnet, like a normal magnet. Let's say you have a bar magnet. which has a north. Sorry about that. Yeah, which has a north pole and a south pole, right? So when you say that the field is moving from north to south, just imagine that this is a magnet, right? So if this is a magnet, then the field would be moving from this point to this point, something like this. So if anything that is also charged and that can interact with the magnetic field were to interact with this field, it would also experience the field in this direction, right? And if it were the other way around, then anything that interacts with this field would interact in this direction. So that's what the direction of the magnetic field generated by the electron also entails, that if anything were to interact with the electron in terms of its magnetic field, then it would be experiencing the magnetic field in the direction in which the magnetic field is being generated by the electron.
Would we consider the magnetic field being up and down in according to the frame of reference, or is it just there's something global that this would be considered an up direction for the spin, and this would be considered a down direction for the spin?
Okay, that's a very good question. So when we talk about frames of reference again, then things become a little ambiguous, because frames of reference in terms of directions in which vectors are applied are something that we take into account in mechanics and in relativity. But when we're talking about particle physics, then having a frame of reference in order to give a direction becomes slightly ambiguous, right? So when we're talking about the direction of a magnetic field that is being generated by the electron, um, I won't say that it's something that's very conventional, but what you can think of is that uh, they're sort of binary options, right? So instead of thinking of them as being independently placed, you can think of them as being opposite to each other. So what happens in atoms is that when an electron is being filled, when the orbitals of an electron are being filled by of an atom are being filled by an electron, then the electrons usually start pairing up, and only if the one electron is going in the spin up direction, it has a spin up, it can be paired only with a spin down electron, because then the magnetic fields would cancel out, so they would not be interacting with each other. So you can usually think of it from a relative perspective, that instead of thinking of the direction as being a fundamental direction or as a global direction, as you mentioned, think of them as being the relative opposite from the respective other state. So if you're talking about up, then think of it as being in a direction that's opposite to a surrounding electron that may spin down. So I hope that answers it to some capacity.
Yes.
I
All
think
right.
Alia has a question in the chat.
Okay. Yeah. Alia asks, what difference would the direction of the magnetic field? What difference would the direction of the magnetic field affect? So I sort of talked about this in the previous answer as well, that when we're talking about the direction of the magnetic field, then we're talking about the direction in which anything that interacts with the magnetic field would be impacted. So when we're talking about again, when we go into the details of the electromagnetic theory, then then we come across things like the left hand rule and the right hand rule, and so on. So the reason why we consider magnetic fields, the direction of magnetic fields, is that if anything that interacts with the magnetic field is going in a particular direction, then it would be deflected by the magnetic field in a particular direction as well. So that direction would be, let's say, direction A if the electron is spinning clockwise, and it would be the opposite of direction A if it's spinning anti-clockwise. So that's the difference that it would make, that if anything was to interact with the magnetic field, or it was going through it, for example, then the direction in which it would be deflected would be opposite in the case of spin up and spin down. So uh, that's not a complete picture, but I hope that gives you a general understanding of what we're talking about.
Yes, thank you.
All right. So anyone else? Any more questions? Okay, if not, then should we move on? Panther, do you want to take the session forward then?
Yeah, we can start with the Higgs boson. Um,
Okay, so is it one of the... Yeah.
okay, so I'll start from here. Basically, it's a bit of introduction to all the scientists who helped develop this Higgs boson. So, and bosons as a whole. So basically, Satyendranath Bose and Albert Einstein, they both created the Bose-Einstein statistics, which basically they theorized a new state of matter. And in that, S.N. Bose, he theorized that there will be elementary particles for forces. That time it was just a theory, and then later Paul Dirac, he first discovered that light is a light. After it was seen that light is also can be a particle, he discovered that other bosons, and then he named it after S.N. Bose. That's why we get the name boson. And then cut to 1964, we get Peter Higgs, who trying to solve the mystery of mass, introduced a concept called that that the mass is given by something called an Higgs field. We'll discuss Higgs field in the next slide. Okay, so next slide. Okay, so first, weight versus mass. Why do we need the Higgs boson? Okay, so weight is a vector property given to us by gravity. Now, vector is something that has a magnitude and a direction. So your weight always points down, like basically where the center of the earth, where your center of gravity, it points down. That's your weight. That's not your mass. So depending on the strength of gravity, we have different weights. For example, we weigh 6 times less on the moon and 2.53 times more on Jupiter. So if somebody is like 100 kgs here, he'll weigh 253 kgs on Jupiter. And if somebody is 60 kg here on Earth, then he'll weigh about 10 kgs on the moon. So that's weight. And I am using the word kg, the unit kg, which is a unit of mass. But so basically, when you stand on a weighing scale to see your weight, what it's doing, it's like it's calculating how much mass would produce that kind of will produce the weight you're putting on the weighing scale. There's a difference. What you're getting is the mass, but uh, yeah, so there's a distinctive difference between weight and mass. So mass is basically a property which gives an object resistance to motion. That is, yeah. Vidush?
Yeah, there was this question that I had in mind just now when you said that we would technically weigh 6 times on a weighing scale, 6 times less on the moon. So how so then there's this question that how do we know for sure that we weigh like we for example, if you said that there's a person weighing 60 kgs, so how does he know exactly that he is weighing 60 kgs on Earth? Like
Okay.
maybe
Yeah. Okay. So you're done with the question? Wait, you wanted to say something
yeah.
else?
No, I
Okay.
just
Cool.
wanted to finish.
Okay, so
You may continue.
basically, what weighing scales do, you stand on the weighing scale, right? And because you are on that weighing scale, which is on the Earth, you exert a force on that weighing scale. That weighing scale takes the amount of force that you are putting, and then it calculates what mass would like a person of that a person exerting that force will have like what mass will that person have, and that's what it displays it. So the 60 kg that you're looking at your weighing scale, that is actually your mass. So for example, in Earth's case, let's consider that the acceleration due to gravity is 10. We know gravitational force is equal to m into a, right? So, so the actual force that you're putting on that weighing scale is 600 newtons. It's when you stand on it, you are exerting a force of 600 newtons, which then the weighing scale calculates that, okay, if it's if I'm getting a force of 600 newtons, then a person of mass 60 would be standing on me. That's how it calculates. So uh, and because the value of the acceleration is there, is intrinsic to the weighing scale. If you take that same weighing scale to the moon, you'll have a different reading, because like the force that you're exerting, you know that it's on a different planet, a different gravitational field, but the weighing scale does not know. So yeah, the way on a weighing scale, the units are actually like it kind of measures weight, but the units that they do is mass. So this that thing. So is it clear?
Yes.
Okay, cool. So where was I? Yeah. So mass is basically a property of an object which gives a resistance from motion. So basically Newton's first law, that if an object is not if an force is not exerted on an object, that object will not move, or if it's moving with a constant velocity, it will move at a constant velocity. So more mass is basically inertia. It restricts motion. But what gives an object mass? That has been a question for centuries. So to explain that mystery, Peter Higgs proposed the Higgs field theory in 1964. Next slide. Okay, so here's a video explain the Higgs field. We'll watch that first.
Should I play the video?
Yeah. Go on.
Just let me know if you can hear the audio.
Yeah.
Without a doubt, the most exciting scientific observation of 2012 was the discovery of a new particle at the CERN laboratory that could be the Higgs boson, a particle named after physicist Peter Higgs. The Higgs field is thought to give mass to fundamental subatomic particles like the quarks and leptons that make up ordinary matter. The Higgs bosons are wiggles in the field, like the bump you see when you twitch a rope. But how does this field give mass to particles? If this sounds confusing to you, you're not alone. In 1993, the British science minister challenged physicists to invent a simple way to understand all this Higgs stuff. The prize was a bottle of quality champagne. The winning explanation went something like this. Suppose there is a large cocktail party at the CERN laboratory filled with particle physics researchers. This crowd of physicists represents the Higgs field. If a tax collector entered the party, nobody would want to talk to them, and they could very easily cross the room to get to the bar. The tax collector wouldn't interact with the crowd in much the same way that some particles don't interact with the Higgs field. The particles that don't interact, like photons for example, are called massless. Now suppose that Peter Higgs entered the same room, perhaps in search of a pint. In this case, the physicist will immediately crowd around Higgs to discuss with him their efforts to measure the properties of his namesake boson. Because he interacts strongly with the crowd, Higgs will move slowly across the room. Continue our analogy, Higgs has become a massive particle through his interactions with the field. So, if that's the Higgs field, how does the Higgs boson fit into all of this? Let's pretend our crowd of partygoers is uniformly spread across the room. Now suppose someone pops their head in the door to report a rumor of a discovery at some distant rival laboratory. People near the door will hear the rumor, but people far away won't, so they'll move closer to the door to ask. This will create a clump in the crowd. As people have heard the rumor, they will return to their original positions to discuss its implications, but people further away will then ask what's going on. The result will be a clump in the crowd that moves across the room. This clump is analogous to the Higgs boson. It is important to remember that it is not that massive particles interact more with the Higgs field. In our analogy of the party, all particles are equal until they enter the room. Both Peter Higgs and a tax collector have zero mass. It is the interaction with the crowd that causes them to gain mass. I'll say that again. Mass comes from interactions with the field. So let's recap. A particle gets more or less mass depending on how it interacts with the field, just like different people will move through the crowd at different speeds depending on their popularity. And the Higgs boson is just a clump in the field, like a rumor crossing the room. Of course, this analogy is just that, an analogy, but it's the best analogy anyone has come up with so far. So that's it. That's what the Higgs field and Higgs boson is all about. Continuing research will tell us if we found it, and the reward will probably be more than just a bottle of champagne.
Okay. So, questions? Yeah, go ahead.
I didn't exactly understand what they meant by a clump of the Higgs field.
Okay, so a clump, consider Higgs field as as a bed sheet. It's tidy across your bed. Now, due to some kind of force, or maybe you throw a ball at your bed, the tidiness gets disrupted, right? And where the ball hits, this becomes a depression. There, the the bed sheet clumps. You can see a depression, right? Similarly, the Higgs boson is basically one of those clumps or depressions of the Higgs field. Normally, you can't see the Higgs boson. Higgs boson are entire because it's clumps in the field, so you can't really see in Higgs boson. And all the operations of the particles, they happen in the Higgs field, and everything happens in the Higgs field. That's why you cannot take that boson out of the field. That's why you can't see the boson. But in particle accelerators, what they did was they collided two particles with a lot of energy, like some like much more, like 10,000 times more than what your typically the mass of the electron or proton is. So it's like and because of that high energy collision, your Higgs field got crumbled, and that's why your bosons were detected. Like people could see that there are some kind of energies, some specific energies, which was um, predicted by Peter Higgs. Those clumps, those so-called properties that they saw in the graphs of like the energy graph, is very similar to a clump in your bedsheet. Is it? Are you getting me?
Yes.
I feel a bit confused on Higgs boson.
I guess
Okay.
that's a very interesting topic, Alia. Panthu, if of course, please address Alia's question, and then I guess we can wind up. You all can share the quiz link with the children for today, because it's
Yeah, but
getting
I just have one
we'll
more.
get tired. Yeah, sure.
Yeah, I
Okay,
just have
Vikram.
one more slide. And
Okay,
Alia, can you
okay, fine.
elaborate your question?
Yes, I'm still a bit confused on the Higgs bosons, bosons because I did not really understand them. I'm unable to understand what are they.
Okay, 1 minute. I'll get a paper and I'll try to explain. Okay, so consider that this paper is your Higgs field. It's like the Higgs field is three-dimensional, but consider that this is your Higgs field. It's uniform, and like particles, they go through the Higgs field, and they get restricted due to Higgs bosons and like other stuff, and because of that, they get mass. Cool. Now, if I take a pen, and this is my particle, and if I like if I puncture it, then here you can see, yeah, there are lumps formed of the paper, and these lumps is basically, if the paper is equal to Higgs field, then these lumps are basically your Higgs bosons.
Okay, thanks.
Did you understand? I know it's a very difficult topic. In fact, it's it's very difficult to explain fields and bosons. That's why Higgs boson and Higgs field is such a evergreen topic even now, after so many years of it being found, because it is very difficult. Don't worry, we'll send you the links of these videos and a couple of more videos, and you can watch it and understand. Yeah, Vidush?
Would we consider the Higgs field being made up of the Higgs boson?
No, no, we can't. Like technically we can. Yeah, technically we can. You have to imagine like it's a sea, and like every water droplet is basically Higgs boson. You can consider it like that.
So if there's a field, there should be something emitting the field, like creating the field around it. If we are calling
Uh,
it a field.
Actually, the funny part is, according like the new theory, the quantum field theory says that these fields exist, and all the particles are just vibrations or clumps in that field. So there's a different field for electrons, there's a different field for quarks, and there's a different field for Higgs boson, and like there's a different electromagnetic fields for photons, and they all exist at the same place. And like, yeah, so basically it's okay, consider it's a calm lake surface. You know that there are a lot of water droplets which creates the lake, and now if you throw a pebble on it, it creates ripples. Those ripples are the particles.
So it basically denies the does it indirectly deny the existence of particles on its own?
Technically, yes. Technically, yeah. The quantum field theory says that nothing is really like the particles, they're all just excitation of their own fields. So every electron in your body is just another excitation of the electron field. Every quark in your body is the excitation of the up quark field or down quark field. And these clumps, any kind of excitation creates a clump. Like, for example, you take a string, and then if you like play with it, so you will get a like you will get a wave like this. And this wave is also a kind of a clump. Like it's not in its normal range, which is a straight. It has a height, and it has a crest and a trough, and that is an excitation. And every excitation is a particle.
According to the theory.
Yes. Okay, so I think somebody asked, what's the difference? What difference does the Higgs boson making a lump cause on the particle? Okay, so the Higgs boson, that lump doesn't do anything to the particle. When the particle moves throughout the field, so it's the Higgs boson does not give particle the mass. The Higgs field gives the particle the mass. Higgs boson, it's just the remnant of the Higgs field disturbance. So that's why people, like the scientists, they tried looking for the Higgs boson because they knew that if the boson exists, there has to be a field for it. And that's why finding the Higgs boson was so difficult, because uh, the Higgs field is everywhere. Yeah, Urjit?
So my question is why, as in why do we, what is the need for a Higgs boson when everything is done by Higgs field? As in, why is there a need to find the clusters of the field?
Okay, so Higgs boson, they only exist inside their fields, right? So if it moving, like in that video, those spectators who are going towards, okay, wait, no, how do I explain it? Okay, so Higgs bosons are just the remnants of that field. You can't you can't observe the field directly, because it's everywhere. You can only observe when there is when there is either a energy difference or any kind of difference. Like when you go to a sabzi mandi, you measure the difference in mass with the weights and your subsidies, or maybe height difference. So in particle physics, like CERN and in case of particles, what you can only observe is energy difference. But if the field is everywhere, so that energy will also be equal, because if there's anywhere more energy, it will eventually even out, right? So that's why in the particle accelerators, they tried creating a very big explosion in like space, which excites the Higgs field, so that so that there's a temporary, very huge energy difference. So basically, if all the Higgs field is like at this level, there's one because of that high collision or something, there's one peak like this. That peak becomes your boson. So that's why they had to now the scientists, because of the energy difference, they can observe this peak. They can't observe the plane field, they can only observe the peak. That's why people wanted to they had to observe the Higgs boson and not the field. Yeah.
So it was just for the sake of actually identifying the existence of the field.
Yes, if there is a field, then that field has a boson. A boson is basically what like it's an excitation which carries that field. So if you have an Higgs boson, that means you have a Higgs field.
Right. Thank you.
Yeah, Madhav, you had you had raised your hand.
No, I had no question.
Okay, so we'll go to the next slide. Next slide. Okay, so your mass is not from the Higgs field. Counterintuitive, but hear me out. The Higgs field gives mass to the elementary particles, but it's only part of the story. The whole mass of a particle is like Higgs field is only part of the story. For example, the mass of a proton is more than the sum of the mass of the quarks. The rest of the mass actually comes from the gluon potential energy in the proton. Like the gluons travel and they also have energies. That energy, because of E equals to mc squared, that also has mass, and because of that, it also contributes. So the rest of the mass actually from the gluon potential energy. Mass is in a way a form of restricted energy. The relation can be explained by E equals to mc squared, Einstein's most famous equation. And so most of our mass is also from the sum of the numerous energies in every atom which make up our body. So the Higgs particle, the Higgs field, that only gives mass to the elementary particles. But once those particles come together and form an object or anything, they also have a lot of energies between them. There's a strong nuclear force by the gluons. There's a weak one. There's the electromagnetic light. Even though they're massless, gluons, gluon photons, they're massless. But still, the energy that those gluons and photons and everything that they had, they also contribute towards the energy. Like for example, if anything that has more energy has more mass. So a hot cup of water is actually more massive than a same quantity cup of cold water, because the hot water has more energy in it. The extra mass is very less, because it's the energy is divided by c square, which is huge, like 9 into 10 to the power 16, I guess. So it's very less. Extra mass is very less. But when it comes to very small particles, where your overall mass is very less and energies are comparatively huge, these add up. So any questions?
I think we can share the quiz now.
Yeah.
I'm actually a little confused.
Maybe we can take up the questions in the next session now, the rest of the questions. Would that be okay, children? It's because it's a little late now.
I guess we can take the questions in the next class. We can give them.
All right, Alia, just children, just keep your questions ready, because otherwise uploading this session will also be difficult. Pampu, you can share the quiz link with me.
Yeah. Devangi, you have the quiz link, right? Can you share it? I kinda can't find it.
I'll share.
Children, it's really heartening to see that so many of you have so many questions, but today there's little, we've exceeded our time limit, so hence sincere apologies. We'll start the next session with all your questions on bosons, and this is the link shared by Divangi. Kindly do answer the quiz questions. Today we have had, this is the second quiz that we're sharing with you, and next session we'll take your questions and discuss the answers to these quiz also.